So if you were at this point, you'd have 0, you'd be at target, even though it's a target range. So what you do is, proportional to how far away from the target you are, you raise these parameters. And then you have to find rules and ways to raise them. But it's always done proportional. That's called a proportional feedback. If you overshoot, then let's say I'm going to do maximum overshoot if I hit this line. This number divided by that number is how far over I went. And so I proportion that and reduce my dose proportionally. Mm-hmm. And that's the way feedback controllers work. Proportional to how far off you are is how much you get back, or how you alter your dosing, your physiologic dosing. In my case, it was altering these constants for this equation. But in my case, I had to describe the curves. And then I had to describe the curve for maximum response and the curve for maximum negative. So this is the curve for maximum positive response, this is the curve for maximum minimum response, negative response. And then you have to have other rules depending on what other restraints you have. And like down in here, when you're real low, you have a restraint is that you don't want to be giving insulin when the sugars are real low. So you have what's called an insulin cutoff. And so the principles of feedback control, proportional feedback control, are understanding how far away you are from your point, and then proportionally changing something. Then the other thing you have to think about feedback control is how often you're measuring versus the response time of the organism, or the response time of what you're trying to change. I'll give you an example. If it took 4 hours for the insulin to work, for whatever it was supposed to do, in this case, lower the sugar, and I changed my model every 15 minutes, you would be changing things so quickly and responses wouldn't occur for another 4 hours. You might make 5 changes, all in the wrong direction. Or the first one's the right direction, all the rest of them will be potentially overshooting or in the wrong direction before the change that you first made kicks in. And then what you do in that situation, you get cycling. So if your target was in here and you were here and you gave a big response because you went out a little bit and you didn't give it the 4 hours to respond, what you do is the cycler, the machine that you generate to control the oxygen in this case, could do this. If you're measuring and responding faster than the organism response or the physiologic response. So that's one, and you've seen harmonics. They're called critical harmonics. If you look it up on the internet, you'll see it. Is it critical? I think it's critical. It's harmonics, control harmonics. And you've seen pictures of bridges that had a wind go by them and and they start, and then they go out of hand and the bridges break up. Same thing. It's exactly the same principles. It's important to understand because it's just like overcorrecting when you're driving. If you're driving and you need to swerve and you overcorrect, what do? You almost tilt one side and you go the other way and you just go like this. So that's how when you learn to drive, you learn to correct the right amounts and you damper your response because you know what overcorrection does. Well, that's what control circuits can do, is they can lead to over-control and cycling. This software, we built into the software this kind of proportional change. We also built into it different kinds of changes when the sugars were down in here. Because if the sugar is in the control range, and you get points in here, you probably don't want to make changes unless there are trends. So if you had a trend of a blood sugar in time slowly going up, you might want to anticipate it going up further by changing the model. If the sugars were going up, you'd want to lower the model. If the sugars were trending down, you'd want to the other way. If the trend is going up, you'd increase the model. If they're trending down, you'd decrease the model. So we put different control circuits down here than we did up here. And then the other thing, some other things we built into is insulin hangs around sometimes. So if a patient's blood sugar was, let's say it was 200, and they're getting a dose of insulin, let's say they were getting 10 units an hour IV, and now I have time across this axis. And then all of a sudden, they check another sugar, and the sugar drops down to, let's say it drops down to 100. And the dose of insulin is 1. Well, the level, if this has been going on for an hour, this level is pretty level, because the half-life of insulin is 3 to 5 minutes. So in an hour, it sort of reaches its equilibrium, and you have a fixed level at a given dose. I'm not going to put a scale because I don't know what the level is, but I know the dose was 10. What happens when the level drops off? I mean, the dose drops off. The level doesn't go like that. You anticipate the level that the dose needs to be down here. But what happens is the level does this, because that's the physiologic removal of insulin from the blood. And this curve is dependent on kidney function. So if you have good kidney function, it does that, and you get about 7%. The area under this curve is roughly 7% of the next hour, that black. If you have bad kidney function, it may go down like this. Go the other direction. The area under that curve may be size 20%, 40%. In other words, I thought I was giving this dose, but I really gave this dose plus 7% of that delta. Or if I had renal failure, it might be this dose plus 20%. So we built into the software the removal of insulin on board. So this is insulin that's in the body. It takes time to get out. Now, oxygen moves a little faster.
Yeah, I'm not sure how fast this one
Quite a
is.
bit more. It's much faster. And it's cleared by the lungs as opposed to the kidneys. So there you're depending, you don't have a measure. We have a measure of kidney function. The measure of lung function is more difficult because there's no blood test for that. Oxygenation may be, but that's...
Yeah, that's where, as we talked about it just a couple of weeks ago, I was kind of thinking through with them the different variables that affect oxygenation.
Yeah.
And so, there's some influence from cardiac output, diffusion capacity, hemoglobin, and so there are some variables that I suppose you could build into models.
And those are the kinds of things you need to quiz your dad on and get him to name the variables, and then try to figure out how the variable affects oxygenation. What's the math between the variable and whatever you're measuring? Because you're going to be measuring something that's pretty simple. Saturation
More simple than insulin.
Yeah, much more simple. So you're going to be measuring something. And you're also going to have measurement errors. You're going to have people that take them off, and you're going to have to build code. You have to build into the software something that's going to pick up when this thing has come off. Because certainly if it was off or all of a sudden making a big change, you wouldn't want to make changes in response to bad readings. So you have to find a way of confirming your readings and getting the readings accurately.